Hello there. In this video, I am introducing the basic procedures for integrating what we call trigonometric integrals. I'm not actually going to be going through and doing any full examples, but rather I'm just going to show you the different types of problems and the basic things that you are looking for to get started. So let's get started. The first thing that we're going to be taking a look at are powers of sine and cosine. And we've already seen some powers of sine and cosine. One example would be, let's say we have the integral of cosine to the third power x times the sine of x dx. In this case, we have a sine function which is to the first power. Another example would be if we had, let's say, the sine to the fifth power x times the cosine of x dx. In this case, cosine is to the first power. In either case, if you have an integral with sines and cosines, and either sine or cosine is raised to the first power, then this is simply a u substitution problem. So in this particular case, you would let u be equal to the cosine of x, and of course du dx is going to be equal to negative sine of x. And so dx is going to be equal to du divided by negative sine of x. And so when we do our u substitutions, you can see that the sine of x is going to cancel out. So the moral of the story here is if you have a sine or a cosine raised to the first power, it doesn't matter what the other function's power is. It could be raised to any power. But if sine or cosine are raised to the first power, this is simply a u substitution problem. Next, what happens if you have sines and cosines, but neither one of them are raised to the first power? Then what we want to look for is an odd power of sine or cosine. So if we have an odd power of sine, what we want to do is we want to strip out a factor of sine, or if we have an odd power of cosine, strip out a factor of cosine from the odd powered term. So as an example, if we had a sine cubed x, we are going to factor that into sine squared x times the sine of x. If we had a cosine to the fifth x, we are going to factor that into the cosine fourth x times cosine of x. So what we are doing is we're stripping out a factor of sine or cosine, that would be this or this, from the odd powered term. All right, the second thing we want to do is convert the rest of the trig functions using the Pythagorean identity. So this Pythagorean identity, which you learned in trigonometry or pre-calculus, is going to be very useful when we're doing trigonometric integrals. And so what step number 2 is saying is we are going to take this term right here, sine squared x, and we're going to convert it into cosines using this identity. We're going to take the cosine to the fourth x and convert it into sines using this trig identity. However, we have one more step to do. Cosine to the fourth needs to be broken down further into cosine squared times cosine squared. And then both of those cosine squareds would be converted into sines using that identity. Then we are just going to do a little simplifying. And finally, I didn't put the simplifying step in there, we integrate using u substitution. These problems will almost always be reduced to a u substitution problem, but we have to use a little bit of trigonometry and a little bit of algebra to get us there. So let me just set up an example. Let's say that we have the integral of cosine to the fifth x times sine cubed x dx. Now they're both odd, so it doesn't matter which one we go with. Remember, we're looking for an odd powered term. I would always go with the lowest powered odd powered term, which would be sine cubed. And so what we're going to do is we are going to simply take the sine cubed and we are going to change that into sine squared x times sine of x. And we're going to write the rest of it down. So we're simply factoring sine cubed into sine squared and sine. And then we are going to take that and we are going to convert it into 1 minus cosine squared x. So we will have the integral of cosine to the fifth x times 1 minus cosine squared x times sine of x dx. And so, as I said previously, we're going to do a little bit of algebra on this, and then we're going to do some u substitution. But for now, I'm just going through the thought process of what you do to get it set up. Okay, let's say we have the integral of sine to the sixth x times cosine to the fifth x dx. All right, so we're looking for an odd powered term. Well, the only odd powered term this time is cosine. So we have to take cosine to the fifth and break it down into cosine squared x, cosine squared x, cosine x, and then the rest of this comes down. And then this and this will be converted into sines using the Pythagorean identity. 1 minus sine squared x, 1 minus sine squared x, and then we have the cosine x dx, and over here we would have the integral of the sine to the sixth x. Then we're going to do a little bit of algebra magic, and then we are going to do some u substitution. All right, next. What happens if with sine and cosine, they're both even powers? If they're both even powers, then we have to use these identities that you also learned either in pre-calculus or trigonometry. We're going to be using these identities a lot. So the first thing we want to do is we want to take the even powered of sine or cosine and convert them using this identity. If we had a cosine squared x, we would use this one. If we had a sine squared x, we would use that. Then we're going to convert any remaining squared factors to cosine, and then integrate using the cosine formula. So, as an example, let's say we have the integral of sine to the sixth x times cosine squared x dx. So notice neither power is odd, otherwise we would use the previous procedure. Both of them are even, so I'm going to look for the lowest power, which would be cosine squared, and I am going to convert that. I'm going to take cosine squared x, and I'm going to convert it into 1/2 plus 1/2 cosine of 2x, a double angle. This is one of those double angle formulas. So we would go over here, and we're going to take the sine squared x times 1/2 plus 1/2 cosine of 2x. All right, so we've converted cosine squares. Now, what about the sine squares? Well, we have to do the same thing there, unfortunately. We have to convert the sine squared x, sine to the sixth x, into sine squared x times sine squared x times the sine squared x. And then each one of these is converted into 1/2 minus 1/2 cosine 2x. So you would have that 3 times. So this would be a fairly complicated problem when you put it all together. And then you would do a little bit of algebra magic on it, and finally it would probably come down to a u substitution problem. A little bit simpler case is when you only have sine or cosine. So let's say we have the integral of sine squared x dx. Keep this one kind of simple. Well, we're simply going to replace that with 1/2 minus 1/2 cosine 2x dx. What if we had the integral of cosine to the 4th x dx? Well, we have to break that into the integral of cosine squared x times cosine squared x dx. And then that would become 1/2 plus 1/2 cosine 2x times another 1/2 plus 1/2 cosine 2x dx. At this point in time, you would perform a little bit of algebra on it, simplify it, and then we're going to be doing a u substitution. Next, we want to take a look at powers of tangent and secant. 2 basic rules to follow here. The first thing you want to look for is secant even. Do you have an even power of secant? And so the simplest case, if you have an even power of secant, let me just go right to an example up here. Well, actually, let me do it here. Let's say we had the integral of tangent cubed x times secant squared x dx. So we have an even power of secant, but it happens to be secant squared. If you have an integral with tangents of any power and a secant squared, this is a u substitution problem. This is a u sub problem. And the reason for that is because if we let u be equal to the tangent of x, the derivative of tangent of x is equal to secant squared x dx. And so therefore our dx is equal to du divided by the secant squared x. And so they are going to cancel out. So this is a direct u substitution problem if you have any power of tangent but a secant squared. What happens if secant is even, but it's to the 4th power or to the 6th power? Then what we want to do is we want to factor out a secant squared. So if we had secant to the 4th, we would break that into secant squared x times secant squared x. And then we are going to convert the remaining secants to tangents. So we're going to keep this one. This is the one we factored out. We're going to convert these into tangents using this identity right here. Secant squared x is equal to tangent squared plus 1. So we would have tangent squared x plus 1 times secant squared x. And then we're going to do some algebra magic, and we are going to integrate using the tangent formula and some u substitution. So let me just give you a quick example of that. So let's say we have the integral of tangent to the 6th x times secant to the 4th x dx. Well, I notice that secant is to the 4th power. So I am going to take secant and factor it into secant squared times secant squared x dx. This I'm going to leave alone. This I'm going to convert to tangents. So I have the integral of the tangent to the 6th x times 1 plus tangent squared x times secant squared x dx. And as always, at this point in time, we're going to be doing a little bit of algebra and then a substitution problem. The last case, when we have tangents and secants, is to look to see if you have a tangent that is odd. So the easiest thing to do is look for secant that is even, then a tangent is odd. Sometimes you'll have an even secant and an odd tangent, like the first example that I gave with tangents and secants. So if tangent is odd, we want to factor out a secant tangent, convert the remaining factors to secants, and integrate using secant formula. So let's say you have, if you have a, well, let's just do an example. I'll just go right to the example. We have an integral of tangent cubed x times secant squared x. Or actually, let's just make it secant x. What we want to do is we want to factor a tangent out of the tangent cubed. So we would have tangent squared x times tangent x secant x. And we're going to leave this alone. And what we're going to do then is convert this into secants. And so we would do that using the trig identity back here. Secant squared x is equal to tangent squared x plus 1. So you may want to write that down. Secant squared x is equal to tangent squared x plus 1, or tangent squared x is equal to secant squared x minus 1. So we would then have secant squared x minus 1, replacing the tangent squared, times the tangent x times the secant x. All right, at this point in time, we would do a little bit of algebra on it, and then we would be able to do a u substitution. So in this video, I have not gone through, as I said, and done any complete problems, but rather what I am doing is just giving you the procedures of what you want to look for. First, do you have sines and cosines? Certain things to look for. Do you have tangents and secants? Certain things to look for. All right, I think this video will be helpful. Keep this video handy. I'm going to be going over these things in class as well as you're going through and doing the homework. Write these rules down, do some examples. All right, I hope you found this useful.